Okay, hey, so this is the limiting reactants video. It's the second in the multimole calculations. It kind of goes ahead with what we started at the end of the last video where we combusted ethane and I had you calculate reactant that was left over. What you're going to do in this one, we're going to figure out, okay, if I have these amounts of reactants, how much product could I get? So for example, we'll take the commonly known equation 2 unicorns plus 3 packets of nerds leads to 4 nerd rope candies. Obviously, because unicorns poop out nerd rope. If you don't know that, you need to look it up. Either way, let's say that in a given situation we have 4 unicorns, and we also have 5 of the nerds, and we're trying to see how much product maximum we can get with that combination. So we'd go ahead and convert both of those to product by multiplying by the ratio. My ratio for nerd rope to unicorn is 4, and I'm just going to abbreviate nerd rope as NR. 4 NR for every 2 unicorns. So with that, I'm going to get 4 times 4, which is 16 divided by 2. I get 8 nerd ropes from my 4 unicorns. And if I take my 5 nerds and I multiply that by the ratio in this case is 4 nerd rope for every 3 nerds. So when we multiply that, we end up with 6.7 nerd rope. So in that case, our nerds, our 5 nerds, are the limiting reactant because they only allow us to get 6.7 nerds, even though with the unicorns, with 4 unicorns, we could have gotten more. Either way, our reaction is limited by the amount of nerds that we have available. All right, so let's look at a real problem. Iron plus sulfur becomes iron 2 sulfide. Question is, if you react 8.5 grams of iron with 6 grams of sulfur, what's the limiting reactant? So your first step, one, you make sure it's balanced. This is, and I'll put ones everywhere just so we're all clear. You're going to go ahead and take each product and convert them to moles, or each reactant and convert them to moles, and then you will convert those into moles of product. All right? So that's our first step. Here we go. I'm going to go ahead and convert 8.5 grams of Fe. We'll convert that to moles by dividing by its molar mass, 55.8 grams for every 1 mole. That becomes 0.15 mole Fe. If we convert 6.0 grams of S to moles, we will divide by its molar mass as well, which is 32 grams for every 1 mole of S, and that becomes 0.19 mole of S. We'll convert both of those into moles of product. However, the nice thing, our product FES, the ratio of all of them is 1 to 1, which means I can go ahead and change from my iron. I can really get 0.15 mole of FES since the ratio is 1 to 1, and from my sulfur I can get 0.19 mole of FES. So which one limited the amount of product you made? Obviously the iron, because it gave you the lesser amount. So that is the answer to your question, 0.15 mole of FES, because my 8.5 grams of iron limited the reaction. How much FES is formed? Oh, we already found that. That will be 0.15 mole. Okay, here's another reaction. This is where you take ammonia and combust it. And here we go. If you have 6.5 grams of ammonia with 7 grams of oxygen gas, what's the limiting reactant? And then finally, how many grams of NO are formed? So our first step always is to balance. I'm going to balance this really quickly. You can pause the video and practice balancing yourself. this will be the way that it works. Okay, so our first step, convert our grams, listed here and here, into moles of that same substance, and then convert them both into moles of NO. Why? Because I know that eventually they're going to ask me how many grams of NO are formed. All right. So with my first step, here we go. I'm going to take my 6.5 grams of NH3. Remember to convert to moles. We do 1 mole for every 17 grams of NH3. Remember that comes from the table. And that's going to equal 0.38 mole of NH3. And then we'll take my 7 grams of O2, put that over 1, and I'm going to divide by its molar mass for O2, which is 32, for every 1 mole. And 7 over 32 is going to give me 0.21 mole of O2. And I'll put that over 1. I'm going to convert both of those now into moles of my product. So I'm going to have to multiply by the ratio. Fortunately for us, if you look here, let me get the pointer. Okay, the ratio of NH3 to NO is 4:4, so we can reduce that to 1:1. So I'm going to go ahead and use that right now. So if I multiply by 1 mole of NO for every 1 mole of NH3, it's going to give me the same number. I'm going to go ahead and write that number up here because I ran out of space. 0.38 mole of NO is how much we can get from our 6.5 grams of NH3. So now we need to see, does our oxygen give us less or does it give us more? That will dictate whether or not it's the limiting reactant. So if we look, our ratio of oxygen to nitrogen monoxide, 5 mole of O2 for every 4 mole of NO. If we do that math, that's going to end up with us having 0.175 mole of NO. Sorry, it's all jumbled now. So let's highlight our 2 answers so far. Oxygen gave us 0.175, whereas ammonia gave us 0.38. So which one gave you the lesser amount of product? Well, that would be our oxygen. Okay? So what does that mean? That means that O2 is our limiting reactant, and then we need to go ahead and answer how much NO are formed. How many grams of NO are formed? In order to answer that, we're going to take the amount of moles of NO that came from our O2, which if we look back, that's 0.175. And then we're just going to really quickly convert that to grams. So I'm going to put that over 1 and convert to our molar mass, or using our molar mass, so I'm going to multiply by 30. And that equals 5.25 grams of NO. Okay? And that's our answer for that question. Next, it then asks how much excess reactant remains after the reaction. Why? Because our 7 grams of O2 really limited the amount of product we could make, because we do know that we had extra NH3. Why? Because if we had used all of our NH3, we would have been able to make 0.38 mole of NO. But we couldn't. We actually only made 0.175. So how much extra ammonia do you have lying around? Well, to figure out that, you go back, you take the amount of NO that you would have formed originally using ammonia. So I'm going to take that number. That was 0.38 mole. That came from how much you should have made. I'm going to subtract how much of it I used I'm going to subtract from that the amount of actual reactant, 0.175, that was converted into product, and that's in moles. Why does that work? If we look back, here we made 0.175 moles of nitrogen monoxide. The ratio of nitrogen monoxide to NH3 is the same, so that's saying that we would have used that many moles of NH3 as well. When we subtract that really quickly, that's going to tell us that we had 0.205 mole of NH3 that was left over. If we convert that to grams very quickly, we're just going to multiply by 17. And that gives you 3.5 grams. That's how much excess you have. All right, for this last one, we're going to go ahead and balance this equation really quickly. We're going to put a 2, a 1, a 1, and a 2. Okay, so if we're going to do like a precipitation reaction to remove some lead from water, you could use NaCl to do that. So let's see how that works. If you take 116 grams of NaCl to try and remove 320 grams of lead nitrate, would that be sufficient to remove it? Well, what you're going to go ahead and do is convert both of them into this product. This would be the solid product formed. I'm going to go ahead and start 116 grams of NaCl. I put that over 1. I'm going to divide by the molar mass, 58.5 grams for every 1 mole of NaCl. And actually I'm going to show this as one complete problem to convert to product. So now I'm going to multiply by my ratio that comes from my reaction, 2 NaCl for every 1 PbCl2. So 1 mole PbCl2 for every 2 mole NaCl. And if you do that math, it says that I could create 0.99 mole of PbCl2. All right. In order to figure out if that's the limiting, we have to convert the other reactant into products. So we're going to convert lead nitrate Sorry for the terrible handwriting. We're going to go ahead and convert that. So I'm going to divide by its molar mass, which is 331 for every 1 mole. And we'll multiply it by that ratio as well. At this point where I'm making that arrow, you could make an equal sign, and you could use the ratio again yourself in a separate equation. Fortunately, the ratio for lead nitrate to PbCl2 is 1 mole PbCl2 for every 1 mole of PbNO3 2. If you do that math, it comes out very close, 0.97 mole of PbCl2. Okay, so which one ended up limiting how much product you formed? Well, if you look, this is the lesser amount of product that came from the lead nitrate right here. So, did you have enough NaCl to remove that from the water? The answer is yes, because you were able to make more lead 2 chloride without being limited by the lead nitrate if you just had the NaCl. And then it says how much excess reactant is present. Well, we can figure that out by figuring out how much of that lead 2 chloride we had formed and taking that difference. So the difference between the two for both of ours, 0.99 mole minus 0.97. Difference of that is 0.02 mole of PbCl2 is our difference. With that, we need to convert it back into NaCl, and that will tell you how many extra moles of NaCl you have. So I'm going to take my 0.02 mole of PbCl2, go ahead and multiply that by my ratio of 2 to 1, and that will give me 0.04 moles of NaCl, which is our extra. And that's all you need for today. Good luck.